Good afternoon to everyone. Today we continue study of oblique shock wave theory. And first question which we will solve is a comparison between two types of shock wave presented on figure 9.14, this example 9.4 from Anderson book. To compare efficiency on transition through normal shock wave and transition through one oblique shock wave and one normal shock wave. We will use theory which was discussed on our previous lecture, all the formulas, and appendix A and B to define flow and thermodynamic properties of gas. If you have some questions, please write in the chat or ask during my presentation. Feel free to ask, because I think this is an essential question, must be clear for everyone to solve work one and to solve some practical applications in gas dynamics. Talking about example 9.4, we have the following initial parameters. We have Mach number before shock wave in case of normal shock wave, and in case of oblique and normal shock wave, case B or case 2. The goal is to decelerate flow to subsonic velocities. Here I will write that my Mach 2 would be smaller than 1, and here in region 3, this Mach 3 is also smaller than 1. The goal of flow passing to the shock wave is usually to efficiently decelerate flow until subsonic velocity. It is done in such a way that flow can enter inside some duct, inside some piping of jet engine, for example, and could be used as oxidizer and working fluid inside working motor for supersonic airplane or other types of supersonic devices. So vehicles that fly with supersonic velocity have to have some device inside to decelerate flow in efficient way inside duct, to use this after inside the engine to burn fuel and to produce additional thrust. So the goal is this, to decelerate to subsonic velocity. After we receive subsonic flow, it can be efficiently transformed in terms of velocity, temperature, and other properties already inside the duct, changing just the geometry of the duct. And this problem of transformation is the main problem, as you will see very soon. First of all, I would like to calculate this efficiency for case 1 when we have entering Mach 1 equal 3. And for this, I will just use appendix B from Anderson book. Just a moment, I will open appendix in this edition of Anderson. Let's see, and I will search for Mach 3 in this appendix. Okay, here it is, I found. We have Mach 3, and we can find corresponding ratio of stagnation pressure according to appendix B, P02 divided by P01, a ratio of stagnation pressure as criteria of efficiency of the flow, according to appendix B, would be equal to approximately 0.33. So this is the result of using of appendix B, or in the same way we can calculate flow according to the theory of normal shock wave. This ratio of stagnation pressure is given as analytical solution, as you might know, right? Okay, so this efficiency is 33%. What does it mean to us? That when flow transits through normal shock wave, it loses almost 70%, 67% of its energy is lost. So if we would like after to reuse this energy inside engine, this would be very small quantity of energy, and we never can compensate with combustion or nozzle, so we can never produce sufficient thrust inside our engine to fly with the Mach 3. What will happen in this case? In this case, we receive smaller efficiency, we receive smaller thrust, and we receive smaller flight velocity. We can say that a typical diffuser that works on just normal shock wave flies with approximately Mach 1.5. From 1 to 1.5 can work in a more or less efficient way, because for Mach 0.5, let me check, we have efficiency close to 93%. So P02 by P01, according to Appendix B, is near 93%. 0.93, which is quite high, right? So we have almost all the energy in the flow conserved when flow passes through normal shock wave. And in this case, we can produce enough thrust inside the engine because we lose just 7% here. But when we lose 67%, like in case of case 1 on your slide, it will be never possible to compensate by combustion. In such case, we need to have a more complex transition. First flow goes through oblique shock wave, one oblique shock wave or several oblique shock waves, gradually reducing velocity, and then it goes through a normal shock wave at the end to reduce velocity until subsonic regime. Let's calculate such case just for demonstration. I will choose arbitrary angle of the body, which produces, for example, I would choose just, let's say, 15 degrees, which is quite typical angle of the body. I would like to remind you that is theta, denoted as theta, is the angle between previous velocity direction and body direction. So it's theta. That describes our geometry. We need this to calculate oblique shock wave. I would like to remind you also that there is another geometrical definition that is called beta, is the angle between previous direction of flow and oblique shock wave angle. One thing before I forgot, you have posted, I think Artur have posted a video on our group. I think it's a very nice video, very interesting video about oblique and normal shock waves and both shock waves. And it's worth to assist. And if you are really paying attention on that video, you will find one small issue inside the video. So let me know if you have found small mistake in that video. So we have defined body angle, we know Mach 1, and now according to theta beta M relation, I can find my angle beta. For this, I will go back. I have such a possibility. Let's see, we have Mach 3 here on this diagram. This is my Mach 3 point, and I have 15 degrees. Probably I will use red color. Okay, and here is my cross section. Right here with the Mach 3, and I will approximately take this value of beta. How much could be? 33. Just guess. Just a guess. 33 degrees. Okay. Going back to our discussion, I will write that Okay, beta is 33 degrees. So it's step one, I define an angle of my shock wave. Right. Now when it's done, I can split vector of Mach 1 in part which is tangential and normal to shock wave. I will write that mn1 would be equal to m1 multiplied by sine of beta. And just a moment, I will try to calculate here. We know that 33 degrees is almost a bit more than 0.5, but I would like to have more accurate value. So I will calculate in the program and multiply by 3. It's 163. It's a 163. First checkpoint to in this calculation to do is the following. This result 163 supposed to be bigger than 1, so it should be supersonic because flow normal component of Mach number. I will make here this schematic. I will write mn1 is that is supersonic before shock wave. If mn1 would be subsonic, if you have a product of sine of some angle to initial Mach number, it will give you less than 1, that something is wrong inside the definition of beta. Okay, so beta should be always have enough value, enough big value to have a product of m1 and sine beta more than 1. Okay, so this is our first checkpoint. It should be supersonic. Now I will use this mn1 value in Appendix B. I will use theory of normal shock wave and using Appendix B from book. Let's see. It's page 1053. I will try to find 163. Oh, it's 1054. I will use approximate value between 162 and 164. And I will see two parameters. First, drop of stagnation pressure, and second, Mach number after the shock wave. I will not calculate now other thermodynamic properties because we have just as input Mach number, so we cannot calculate pressure, temperature, or density just having no thermodynamic properties as input. Okay, let me see. It's approximately okay, 0.88. I will make rounding. Of course, we can do interpolation, but we also can calculate by formula. But just as a demonstration, I will write here. So this region 1 here, this would be our region 2 and region 3 at the end. P02 divided by P01 from Appendix B. As a reference, I use my Mach number 163 and is equal to 0.8. So I have still 80% of my energy and I lose 20% on this transition. And to calculate how flow passes through the second shock wave, we need to calculate Mach number 2, which is here, M2. And for this, we need to calculate normal component, this small vector here, which is Mn2. Okay, I hope it's visible still on your screen. At least for me, I see translation to another computer and I see that the quality is good enough so you could see. Mn2, this small vector after flow passes through shock wave. And I also use as a reference M2. I use this reference of Mn1, and using appendix B, I see that it will be approximately equal 0.66. Pay attention, because in your work one, you calculate all using formula, because exists formula, right, for this calculation, and I use just appendix to calculate fast. Pay attention that this value which you receive M normal Mn2 after oblique shock wave should be subsonic. Normal component is smaller than 1. So this is another checkpoint to make, that Mn2 after oblique or after normal shock wave is always subsonic. So we have this transition through normal shock wave, because, okay, it's normal to normal component of Mach number. And now I can calculate Mach 2. According to formula from the book, Mach 2 would be equal Mn2 divided by sine of beta minus theta angle. I will calculate here, which is my difference. Beta minus theta is 18 degrees, right? 18 degrees. So let's calculate sine. Take reverse value. And multiply by 0.066. It's 2.14. 2.14. It's 2.14. Also must be supersonic, because we know that after oblique shock wave, flow remains supersonic. This is the third checkpoint for you. So value is 2.14, and same Mach number M2 as we calculated at the after oblique shock wave. Also we have at the entrance before normal shock wave is also M2. Now I will use just appendix B to calculate oblique shock wave properties for value 214. I see 215, so I will use this closest value. I will not make any kind of interpolation. I see that on this transition, P03 divided by P02 from appendix B would be 65%, 0.65. Okay, and the Mach number M3, according to appendix B, would be 0.55. 0.55 is subsonic, right? Should be subsonic, because normal shock wave can produce only subsonic flow after. Okay, this one is subsonic. Good. Mach in case one, we did not calculate Mach number, so I will add here then that M2 according to appendix B for case 1. Just a moment, let's see, it's 0.48. 0.48. Almost half speed of sound in case 1, and a bit more than half of speed of sound in case 2. Now I would like to calculate total efficiency on case 2. To calculate total efficiency, P03 divided by P01, I will multiply P02 by P01, efficiency transition on oblique shock wave by P03 by P02, efficiency transition on normal shock wave. Okay, these values I already have. I will just make a calculate product of these two values. Okay, just a moment. I multiply 0.8 by 0.65, 52, 0.52. Okay, that's the efficiency on case 2. 52%, so we lose 48%, we keep 52% of energy. In case 1, we lose 67% and we keep 33% of energy. Quite visible that when we have a more complex flow structure, oblique shock wave and normal shock wave, we can keep more energy of the flow, almost 20% more energy, right? That's quite good. But however, it's not enough, still not enough energy. We lose almost half of energy in our flow. I think it would be very difficult to compensate by combustion and to create enough thrust in this case. So for Mach 3, usually we need to have more sophisticated flow structure. This more sophisticated flow structure is, for example, 3 shockwave diffuser is case very similar to work 1 when we have geometry that creates 1 oblique shock wave. Then we have change of geometry which creates 2nd oblique shock wave. Okay, and then we have normal shock wave on the entrance of diffuser. In this case, we can find efficiency on transition through 1st oblique shock wave, 2nd oblique shock wave, and then transition through normal shock wave. Finding product of these efficiencies, we will find total. And definitely for 3 shock wave structure, we'll have much higher efficiency. Much higher efficiency. Can be 70, 80, 90%, depend on optimization of angles. Now, let's see about optimization. We will discuss soon. But before, I would like to pay some attention on comparison between flow over wedges and cones. Please do not forget to ask your questions if you have some about our discussion. Okay, that's the case which I already explained to you. This is how it looks like, diffuser or inlet device which has normal shock wave, just simple tube, right? And the case B with oblique shock wave. To have oblique shock wave, we need to use some kind of central body, or if it's not symmetric, we need to use geometry of our body inclined with respect to flow to create first at least 1 oblique shock wave, and then flow goes through normal shock wave. In such case, efficiency is much better. Much better. So going to comparison between cones and wedges. Wedge is a 2-dimensional structure, is the model which we just discussed, is velocity which has 2 components, and the 3rd dimension is infinite. So we have just this planar planar structure. It can be called a wedge or can be called a corner. From our previous discussion, we saw that from computational point of view, will be no difference if we see not symmetrical structure, but we just see a half and we have a wall here. Okay, so computationally it's absolutely the same. Just wedge is symmetrical and corner is not symmetrical. It's just one side of angle theta. Calculation in such case is known, right? We can provide such computation. Needs to use Mach number before flow changes and the theta angle of the body. Then we use theta beta M relation. We find angle of the body. You can see it in our diagram. And then provide all calculations as I just showed you on previous example. When we see a second case, flow over cone, cone is a three-dimensional structure, is a rotational body. In this case, flow is different. First, flow lines or path lines after shock wave, they are curved because area of the flow is changing significantly once you calculate it as a function of radius r. You can find that area changes with respect to square of radius, right? Where in a case of wedge, so S is proportional to R square, literally PR square, right? And when we are looking to wedge two-dimensional flow, planar flow, and we see its coordinate y, for example, we see that here area is proportional to y in the power of 1. So the way of changing this area is different for wedges and cones, and as a result, we have different behavior of flow lines after shock wave. Before shock wave, all flow lines for both cases are parallel. After shock wave, flow lines behave different. In the case of cone, they have this curvature on the first part of line trajectory. First line trajectory. Also, we may observe that for same flow condition, for same Mach numbers before a shock wave and same angle of wedge and cone, angle of shock wave in case of cone is smaller than in case of wedge. Okay, for example, here for cone is 37 degrees, for wedge is 53.3 degrees. Cone is smaller. It's smaller because the area is increased proportionally to distance in radial direction in square. Right, where in wedge case it's proportional just linearly. When we are talking about model of calculation for cone is completely different from case of wedge. In such case, flow model is not does not consist just of algebraic equation, like in case we saw previously. In this case, we have a system of differential equations, ordinary differential equations that must be solved as a function of coordinate, of x coordinate, for example. And since this model is complicated, we are not studying this model in our classical subject of gas dynamics. This model is not, this model is known, very well known because it's used in many applications, and we can use it. It's published. We can use it, but for just didactic or demonstration of such physical process, we do not use it because it requires solution of number of differential equations. Is not so fast to show in class. In general, this model is not that complicated. Anyone could use and solve and find the geometry of shock waves and the thermodynamic and flow properties when flow passes through these shock waves. Please let me know if some questions appear. Example, sorry, I have some problem here. Example 9.6 is about calculation of drag coefficient when flow passes through the wedge. How to calculate drag coefficient? We need to calculate drag, divide by dynamic pressure and characteristic area or size. This size for us is C, as denoted on the picture. Because it's b-dimensional structure, we just use C as a reference area. And we can perform such calculation. We know angle theta, 15 degrees. We know Mach 5 at M infinite, right? And we can do this calculation. Let's have such an example. We need to calculate transition through oblique shock wave. After oblique shock wave, we calculate pressure. Pressure is distributed uniformly along the surface, along the side surface of this wedge, and behind we have pressure 1. It's a pressure. Okay, maybe I will remove from here M1. Okay, and we have pressure 1. Back pressure is approximately equal to infinite pressure, P1. Let's calculate analytically first how drag and drag coefficient could be calculated. First of all, we will neglect all friction forces and presence of boundary layer. It absolutely has no impact because in such case, Reynolds number is extremely high, is almost infinite, and we know that in such cases, shear stress would be proportional to 1 divided by Reynolds number. It's tau. I will make it better looking. So since a Reynolds number goes to infinity, that show us that its shear stress goes to 0, approximately 0. We will consider just pressure forces in such calculation. Drag force is a force that is directed horizontally, right? And is a total force over this body. So I will project all my forces on x-axis, see, right? And I will see that projection of P2 on the upper and lower side will result in such distribution of force going against my wedge. Okay, this which I draw here is pressure projection of P2. Projection of P2, and I can calculate that. Okay, we have theta, we have C, and probably it's tangent. Okay, yeah, this size here. The drag would be size of the body, or okay, pressure difference multiplied by size of the body. P2 minus P1 multiplied by 2 tangent of 15 degrees. I hope it's correct. Yeah. Why 2 tangent of 15 degrees? Because 1 tangent of 15 degrees is upper side, and the same other one we have on the lower side. So we have formula for drag, and I will also find drag coefficient. CD is drag divided by Q infinite C. I forgot to multiply by C, of course. Multiplied by C here. And now it will be how we can express Q infinite as density infinite. 2 will be here. Velocity infinite and squared multiplied by C, and here I will have my P2 minus P1 multiplied by 2 tangent of 15 degrees C. I can cancel C probably, and I can join 2 and 2, right? Multiply would be 4. So CD would be 4 P2 minus P1 tangent of 15 degrees divided by okay, rho. We don't have infinite, we have just parameters on 1, right? Rho 1 velocity, sorry, 1 in square. I'm already thinking how to change this velocity to Mach number, and we can do it. We can write that velocity is a product of speed of sound and Mach number. So I will use this m in square multiplied by a in square. And let's try to see what else we can have here. Product of density 1 and a in square is density 1 and a in square is gamma RT, right? Yeah, gamma RT. And this has subscript 1. Okay. R is constant. Product of gamma RT, does it give us something? Yeah, it's pressure, right? Because due to equation of state, pressure is density gas constant multiplied by temperature. Okay, so this is same as gamma multiplied by pressure. 1. I will remove this part here. I will remove density 1 and A, and I will substitute. I will put gamma here and pressure 1 here. So we have pressure in numerator, we have pressure in denominator. We see that here on the upper, just let me change color to be more clear. We have this in upper part of our equation, dimension of pressure, and in the lower part also dimension of pressure. It will be cancelled. All other parameters we have in calculation of CD are dimensionless. So as a result, our drag coefficient would be dimensionless, and I hope we have correct. We have correct solution. We just need to know pressure, and all other parameters we know. So let's calculate pressure 2 after after this, or relation between pressure 1 and pressure 2 after this oblique shock wave. As a reference, I will use Mach 5. So for Mach 5, I see beta. Let me go back to diagram. Let's hope that there is some. Okay, here not so convenient. Probably this diagram would work better. We have Mach 5, 5.5. Probably it's 5. Ah, no, there is Mach 5 here. So this curve here, and I need just to find our 15 degrees. This here. Oh, this 15 degrees is right here, this point. So I have approximately 24. I will use 24 degrees for beta. Let's go back. Okay. 24. Now mn1, which is 5 multiplied by sine of 24 degrees. Just a moment, I will calculate. $203. Okay, our checkpoint number 1, this value is supersonic, as should be. Now I look in Appendix B, this value, and I will see pressure ratio. Let me check. 203. I can find 205, so I will use it directly, 205, not 203. And I see my pressure ratio is 4.73. 474. Pressure 2 by pressure 1. We have this inside our Appendix B. I use Mach mn1 as a reference, and I find this value, 474. Okay, it means that pressure 2 is 474 multiplied by pressure 1. You can see that even pressure 1 is directly a value of pressure is not so important here, because all we can calculate independently on value. Now I substitute inside CD. P2 minus P1 will be for us 374. And P1 and P1 I will cancel. Just a moment, I will write you if it's not so clear. I will write you here. CD would be 4 multiplied by 374. P1 tangent of 15 degrees. I hope it will be correct, because I'm not looking to any kind of other notes, trying to elaborate in a way that looks correct. If you see some error in my calculation, please let me know, because I always can mistake, or like any of us, and since I'm solving this without looking to any kind of other notes, this mistake is okay, can appear naturally. M1 in square and P1. Okay, I cancel P1 from upper and lower side, and probably it's time to calculate, because all parameters are known. Just a moment, I will start calculation on my computer. Tangent on 15 degrees is small value, We multiply by 4, multiply by 374. We divide by gamma, which is 1.4. And we divide by 25, it's Mach square. Zero 11. Maybe this is correct. I hope it's correct. I hope it's correct. At least it's not so big and not as one, for example, as we had for cylinder, because cylinder is a blunt body, right? It has a strong ball shock wave problems related to normal shock waves. Here, since we do not have normal shock wave, we have a very smooth transition of our flow. P2 is not so high, just almost 5 times. Okay. Flow is hypersonic, so pressure rise is not small, but is not huge, right? And our drag coefficient is 0.11. You can see that to calculate drag coefficient using shock wave theory, we do not need any thermodynamic property. We need just to know geometry of flow. This 15 degrees was very important because we calculated the angle of shock wave, and we need to know Mach number before shock wave. Also very important because it's used inside calculations. You saw I made transition from just value of pressure. I made transition from density and velocity to dimensionless parameter as Mach number, and it worked quite well. It worked quite well. We do not need any thermodynamic property to calculate drag coefficient, just geometry of our body and dimensionless criteria of velocity as Mach number. I hope it's correct. And I hope you understood, because I see no questions. But still, I expect for some questions. If they appear, let me know. We can return to this discussion if you find some error in my calculation, and we can discuss and calculate more. I think important for you to understand how this is made. Okay, you can ask your questions until the end of the lecture. So meanwhile, I will continue speaking about shock waves. Another important topic is the shock wave interactions and reflections. What is it? Is when we have a complex body like airplane, right? Supersonic airplane or hypersonic airplane is a very nice looking structure, looks perfectly, right? And it might have several parts of the body. Geometry is complex, and shock waves generated by one part of the geometry can interact or with the body, can touch body, or can interact with other shock waves and then touch body. So it's an important question, because once two shock waves are intersected, or more than two shock waves are intersected, they create another shock waves with the structure that we can calculate analytically. You may find in our book such examples. We will see, I think, 2 or 3 different examples on shockwave interaction and reflection, and you will, I hope, understand this idea. Anderson does not give a lot of examples how to calculate, because interaction of several shock waves is a process, is an iterative process, does not have a direct analytical solution, but I can show you idea how this calculation, how this model and calculation process can be organized. In general, it's not so complicated if you would like someday to calculate. can do it easily. But because it's, again, iterative process, not linear equations cannot be solved directly analytically, Anderson does not pay so much attention to show of solution of such flow. Let's discuss first the simplest case when shock wave is generated at point A. At this point, we have change of geometry. It was parallel to flow before point 8, and after starts to have angle of body theta, generating some oblique shock wave. This oblique shock wave reaches another body at point B, and at point B it reflects from the body. Okay, it's causing reflected shock wave, and this reflected shock wave has some properties that we might be interested to calculate. For example, for real applications, for example, you have a diffuser. Diffuser generates first oblique shock wave, and then on the other side of diffuser, this shock wave will reflect. And here in zone of point B, we might have high gradient of temperature, some pressure change, significant pressure change, but mostly temperature, which is important here because we can have, we still have losses, right? And all energy is transformed to thermal energy, and in point B, it's high. This transformation could generate high values of temperature. From structural point of view, we needed to calculate and need to predict these values. It's very important for structural design. As you might find here, Anderson shows beta 1 as angle of shock wave, right? Beta 1 on lower part of our image, and same beta 1 is on the upper side of image, because lower and upper surfaces, they are parallel to flow before shock wave. It's not always such a condition, it's just simplification that Anderson shows. So we have beta 1 in case of lower and upper angle. After shock wave reflects, we do not have beta angle anymore. It's not like reflection of light or reflection of just sound wave, which is reflected on the same angle. For example, light is reflected on the same angle as it comes to body. In case of flow, reflection angle is always different from incoming angle of shock wave, and it happens due to nonlinear physics, nonlinear process of especially compressible supersonic flow. Just a moment. I need to get some water. Okay. Let's make such calculation. What we need to understand here, it's one aspect that would allow us to calculate. We already know how to provide calculation at point A, right? So first, oblique shock wave will not be a problem to calculate. Mach number, thermodynamic properties, and others. What happens with reflected shock wave? What we need to consider, for example, as theta. Theta in such case is shown here in volume 3 and in volume 2. We might find here definition of theta. We have to remember that after shock wave, flow continues to go according to direction of the body after the shock wave. So after second shock wave, flow becomes again parallel to or horizontal. So this is one line to find theta. And another direction that we must consider is direction between first and second shock wave. This direction is same as the direction of the first body. Okay, so these two lines are same. So this is why this angle here is also theta. And since theta is the angle between previous and next flow direction, we can find that theta remains constant for region 2 and region 3. So we have in our calculation to use same value of theta in region 2 and region 3. This is something that simplifies a lot calculation. Let me remove all these lines. Not necessary for now. And I would like to give you an example of such calculation. Let's assume some values. For example, we can start with Mach 1. We have denoted numbers of regions, so we can start with Mach 1, 3. Okay, it's nice. Theta 1 or theta would be 15 degrees. Let's also calculate, for example, pressure. To calculate pressure distribution, or no, better temperature. Temperature is better because I told you that temperature plays an important role in mechanical and structural design. So material should sustain this high temperature. Let's assume that temperature at region 1 was 300 Kelvin, just for simplicity. 300 Kelvin, something that we have normally, normal conditions, right? But in this case, we have Mach 3 times bigger than speed of sound, and normal temperature, 300 Kelvin. Let's calculate. First, as always, I will see beta 1. According to theta beta M diagram, beta 1, let's go back. It's very nice because we can always go back and we can see our previous slides. It's perfect. So I see my Mach 3 and 15 degrees, right? So we already defined this, how much was that, 33? Yeah, I think it was 33 degrees. I already had this example before. Yeah, 33 degrees. So beta 1 is 33 degrees. Just let me check how much we had. Yeah, we had 33 degrees here. Here in this example, we use again 33 degrees. Okay, now I calculate Mn1. It's a product of M1 and sine of beta 1. I think we can use from previous calculation. Let me see. Did we have? Yes, it's here, 163. This value, I will use previous calculation. $163. And we need to calculate now transition. Normal, Mach number after. And what else? Temperature ratio. And temperature ratio I did not calculate on this example, so we will need to go to see it in Appendix B. Let me see. Mach 2 after this oblique shockwave is 214. M2 is 214. So you see how simple we made this example just using data from previous calculation. I do not need to go many values from Appendix A and B. But for temperature, I need. So I will go to Appendix B. I will search for Mach 163. It's between 162 and 164, and I will see temperature ratio approximately is 141. Temperature 2 by temperature 1 using appendix B, and this MN1 as a reference is 141. Okay, now temperature 2 is 300 multiplied by 141. Yeah, I can calculate analytically, but need to check. 423 Kelvin. Okay, that's the temperature after shock 1, after oblique shock wave 1. So all this surface here, which I mark, suffers these temperatures. So it must sustain at least 423 Kelvin, at least because we do not consider boundary layer. On boundary layer, we have higher temperature because velocity stops at the boundary layer. But in the case of this example, we do not see presence of boundary layer, just for simplicity. And now we can calculate transition on second reflected shock wave. I will again go to see my angle of the shock wave in case is phi. Oh, how is written from appendix from the book. Let's see if we forgot something. Yeah, we forgot something, that this one is beta 2 or beta, okay, beta 2. Here is angle between previous flow direction and shock wave. I will see it by theta beta m relation, and phi will be defined as beta 2 minus theta. Just let's go to see diagram 163. No, not 163, sorry. 214. This is our Mach number before second reflected shock wave, 214. Probably would be better to go to more detailed. Let's see here, it's 2.1. There is a value of 2, value of 2.2, so it's somewhere here. Oh, somewhere here, close to 2.2, somewhere here. And theta is also 15 degrees. Okay, let me raise this line here. Is this line, and I will try to find it approximate intersection like this. And then I will find the angle, 42, approximately 42 degrees. If we need an exact value, we solve theta beta m equation. If we need approximate, we just use diagram. So beta 2 is 42. And phi would be 42 minus 15 is 27. 27 degrees. So we have 33 degrees of beta 1 and 27 degrees of phi. You see it's smaller than forced shock wave angle. And since it goes according to theta beta m relation, there is no such a linear relation between one shock wave angle and the other shock wave angle. It must include also definition of Mach number, value of Mach number, and all consequence, so not linear. Okay, I have beta 2. I can calculate using this beta 2 my Mach normal on from region 2 to 3, and 2 I will calculate as m2 multiplied by sine of beta 2. So should be below. Okay. Let me see how much is. $143. $143. Okay, supersonic. Very nice. We expect something supersonic. Now I search this 143 in appendix B, and I will find my MN3 from this appendix B. Okay, is there some 143? There is 144, 142. I will take in the middle. Two parameters. I will calculate Mach number and I will calculate temperature ratio. Mach number is 0.73. Okay, and temperature ratio T3 by T2 would be, let's see, 127. 127. So 27% more than temperature 2. From this value, I can calculate M3. Okay, M3 is MN3 divided by sine of phi. Sine phi is already difference between beta 2 and theta. And temperature 3. Temperature 3 would be temperature 2 multiplied by 127. Let me calculate also this parameter, this value. .6 is Mach number. .6 and temperature 537. 537 Kelvin. This is the temperature after second reflected shock wave. So this temperature we can observe on this red surface, which I mark here. And this I remove. So this is all temperature 3. Okay, and this lower surface is temperature 2. Before, here everywhere we have temperature 1, and here we have also temperature 1 before shock wave. So you can see how different could be temperature after a second reflected shock wave, almost 2 times bigger than before. 537 Kelvin. Material should sustain this temperature when we are doing mechanical design or making choice of materials. Another case is the real, not the real, sorry. Okay, let me make some kind of introduction to this. If the shock wave can reflect, but the shock wave will not have possibility to make second reflection. When shockwave will make second reflection? When it can have intersection on theta beta M diagram. For example, if I have here on zone 2 very small Mach number, for example, let's see, Mach 1.2, okay, let's try. Mach 1.2, for example, I obtain here because my geometry or my initial Mach number gives 1.2 in zone 2. What will happen next? I will try to search cross-section or solution of theta beta M relation or cross-section on my diagram, which correspond to this Mach number. Let's see. My Mach 1.2 here, I mark by red line, does not have any intersection with 15 degrees. It means that if we have Mach 1.2 and 15 degrees of theta, it will never produce oblique shock wave reflected. There is physically no reflection between curve of Mach 1.2 and 15 degrees of theta. As you can see here, there is a huge distance between these curves, so they never intersect. In such case, we will never have oblique shock wave, and instead of oblique shock wave, we will start to have partially normal shock wave. As you may see here, this is normal shock wave. As flow adapts, real flow adapts, and creating instead of oblique shock wave, it creates such a flow structure, which is complex structure, cannot be calculated analytically. This shape of reflected shock wave, okay, which you can see here, can be seen in experiment and also can be seen on a numerical simulation. But unfortunately, such shape cannot be calculated analytically. But we already know how to predict analytically if such problem will appear or will appear just reflection of oblique shock wave. We see theta beta M diagram. If there is intersection of angle of body and Mach curve, it means that oblique shock wave will reflect. If there is no intersection, it means that will appear such a complex shape shock wave that cannot be calculated analytically. We can stop this calculation. We can say that, okay, instead of using oblique shock wave theory on this transition, we can use just normal shock wave theory. We can approximately predict position of this normal shock wave. It will be always displaced against flow in some distance. How much? It's cannot be determined analytically, but we will know that it will be always displaced against flow, and we'll have this normal part. Okay. And transitional normal shock wave, because it's perpendicular to flow, we can calculate using normal shock wave theory. Can consider this a normal shock wave, and all flow properties in zone 3 can be calculated just using normal shock wave theory, but not oblique shock wave theory. This can serve just as a reference, cannot serve as a definitive final result of calculation, because as I told you, this shock wave has not a linear or completely normal structure to the flow. That's the problem. I see today people understand everything I say, or have no questions because of some other reason. I prefer to think that you understood what I explained today. The last case for today, we will start, but I will go I will also continue to explain next time, because this kind of problem requires quite big time. I will just give you an introduction to such case. This case shows to us intersection of two shock waves. One shock wave is generated by upper side, by upper body. It has some inclination angle θ2, which you can see in this picture. Since body changing, this oblique shock wave B appears. Thank you, Luis. And the lower side of the body changes at point G. Geometry starts to have angle θ1 with respect to previous flow direction, and also generates shock wave A. Okay. These two shock waves are a result of interaction of body change and supersonic flow. They definitely would meet at some point. There are several questions which might appear in this task. Okay, such problem can happen in many different aerospace applications when you work with complex geometries, not just from the lower side, but also from upper side. When you generate two shock waves, these two shock waves go in different directions. They are not parallel, so they definitely will meet. If we work inside a closed duct, like you see here, these shock waves will happen, the interaction between shock waves will happen also inside this tube. And we need to predict where it will happen, which flow properties will be, where flow will go after, and others. As Luis told, the class is quite dense today, so I will give you a model and explain how to calculate by this model next time. Today, I just give you very fast introduction so you can think about this problem, and next time we discuss inside the model. So shockwave A and shockwave B meet at point E inside. As we might imagine, because angle θ1 and θ2 are different, they reflect our flow differently. So shock wave A and shock wave B, they are not equal. They also have different parameters. They have different inclination of beta angle. And after inside volume 2 and volume 3 have different flow properties, different thermodynamic properties, different Mach number, and of course, different flow directions, right? Different flow directions. Then, when these two shock waves meet at point E, what happens? These shock waves reflect one from another. They reflect one from another, and they generate shock wave C and shock wave D. Okay, this shock wave C and D, they are also not symmetric. They have different properties. And after this C and D, we have, let's say, a flow volume. I will mark you here. This flow volume, which does not have shock waves anymore. Okay, we will assume that the shock waves C and D, they go and they reflect after from some surface, or they do not reflect, they exit from duct. It's not important for us. For us, it is important to understand how to calculate parameters inside volume 2, volume 3, and especially how to calculate parameters inside volume 4 and 4 prime after these two shock waves meet. We see that there is one common or two common properties, at least. No, first we see just one common property for these two flows, for volume 4 and 4 prime. These common properties are direction of the flow. flow direction inside volume 4 is absolutely the same as flow direction inside volume 4 prime. These two volumes, 4 and 4 prime, they are separated. They do not mix at all. They absolutely do not mix. They are separated by so-called slip line. This line is, let's say, some kind of virtual line that does not exist in real life, but these lines it's a streamline which prevents flows mixture. So these flows do not mix. According to theory, according to experiments and simulation, we might find this property of slip line. So flows do not mix, and both of these flows go in the same direction. These two conditions give us all information we need to know to calculate such a flow structure. First, flows go in same direction. It means that angle of the body, okay, I will call it alpha. For simplicity, is not shown here. Alpha is same for both flows, so we know where flow will go in upper and lower. We will make a balance, and we will find this alpha. And second, the consequence from this first statement that alpha is same is that since there is no change of direction between 4 and 4 prime, it means that there is no pressure gradient which would cause this change of direction. So pressure 4 prime is equal to pressure 4. These two static pressures are equal because flows go in parallel. If pressure would be different in 4 and 4 prime, flow will start to go from one volume to another due to this pressure gradient. Since flows go in parallel, there is no pressure gradient and pressures are equal. So there are two conditions. Alpha for volume 4 is same as alpha for volume 4 prime, and pressure for volume 4 is pressure for volume 4 prime. Unfortunately, Anderson does not give us the model of such calculation, but I think on next class we can elaborate and you will start to understand better. I think it's important, this is why I'm giving. You will start to understand better how to calculate such a complex flow analytically. Okay, I think that was enough information for today's class. Please let me know if you have some questions next time we continue. And I think next time also I can explain you better some questions if you have about work 1. I will try to show you how to format some data. What would be the nice way to show to some representation of data. Nice question, Luis. Do they also have same speed? No, these flows do not have same speed. They have different speed, different Mach number, different velocity. If flows have okay, they have different velocity, but since we do not consider shear stress, because of velocity gradient, we do not see mixture between these two flows. We do not see vortices formation. Not just us, but according to theory, there is no vortex formation, because if it would be free turbulence and vortex formation between volume 4 and 4 prime, it would be impossible to calculate analytically, and we need to make a number of simplifications to find analytical model. But in real life, of course, since there is a velocity difference, of course, there is formation of free turbulence. Okay, guys, please let me know if you have more questions. I will remove all these notes here because they are not so much important in our next discussion. I will just leave these conditions which you need to know, and from this moment we can start elaborating the flow model. Oh, something still remains on the screen, but I already removed. Okay. Okay, people, thank you very much for participation. We will continue next Tuesday, our usual time. About the density, no, density is different as well. Density is not same, just pressure is same. Pressure says us about forces of that initiate or let's say provoke acceleration. Since velocity, since velocity directions are same, there is no acceleration in normal direction. There is no acceleration in direction perpendicular to slip line. Okay, and because of this, pressures are same, but densities are different, velocities are different, Mach number are different, all different. Just pressure is same, and the angle of direction of the flow is same. But we do not need anything else. We just need these two. We can use just these two conditions and elaborate all the complete model. It's very interesting that not so many things are required to elaborate flow model for this case. Please prepare your questions about work 1 for Tuesday, and we will discuss on Tuesday. We still have good time to, let's say, 2 weeks, right? No, not 2 weeks. No, more, much more. Almost 6 weeks to deliver work 1. Okay, thank you very much. See you next week. Have a nice weekend, and thank you for participation today. Bye.